All right, so we're going to start by wrapping up this problem from last week. You're traveling 60 miles per hour in your car down the freeway. Suddenly a refrigerator falls into the road and you have to make an emergency stop. And we want to figure out how much distance is going to take you to make that emergency stop. Right now, a lot of you said 10 car lengths or 8 car lengths, so we're going to see how that works out. Okay, so here's the part of the problem that we already went through. We drew the picture, we introduced the moments of interest. There are 3 moments of interest. Moment of interest 0, you see the fridge. Moment of interest 1, you begin to brake. Moment of interest 2, your car comes to a stop. Okay, so we made the figure. At each moment of interest, we introduced our kinematic variables: position, velocity, time, right? And down to the side here, we introduced symbols for the accelerations we're going to need. We have acceleration A01 between the time you see the fridge and the time you hit the brakes. And we have acceleration 12 from between the time you hit the brakes and the time that you stop. All right, so our next step is going to be to fill in the values that we know. So we can just put the origin at this position here where you see the refrigerator. So x0 equals 0. V0 60 miles per hour. Let's start at time 0. Right? X1, so this is where you hit the brakes. We don't know that yet, we'll have to compute it. The velocity when you hit the brakes, still 60 miles per hour because you haven't started to brake yet. And the time given is 0.5 seconds. Okay? Now the position where you stop, that's what we're trying to figure out. The velocity when you stop is 0. And we don't know the time when you stop. All right. So we'd like to try, now we have to put in the accelerations. So between the time you see the fridge and the time you hit the brakes, the acceleration is 0, right? You haven't started braking yet. As you're slowing, the problem states that the acceleration is, well, you decelerate at 0.7 g, right? So you're moving to the right and getting slower, which means your acceleration is actually to the left, in other words, negative. So we'll say A12 is minus 0.7 g. Okay, now before we proceed with the calculation, we might want to have clean numerical values in MKS for 60 miles per hour and for 0.7 g here. Okay, so leaving this conversion as an exercise, 60 miles per hour is 26.82 meters per second, right? And then we have A12 equals minus 0.7. Substitute g equals 9.8 meters per second squared. And we have the acceleration as you're braking, minus 6.86 meters per second squared. Okay? So to do the calculation now, let's start by figuring out how far you travel before you hit the brakes. Right? In other words, we want to find x1. Well, from moment 0 to moment 1, that's actually a constant velocity process. The acceleration is 0. Okay? So to get from moment 0 to moment 1, we can just use the same formula that we used for the constant velocity problems, namely x1 equals x0 plus v, let's make that v0 here, t1 minus t0. Okay? x0 we'll take to be 0. D0 take to be 0. And that gives us x1, doing substitution. V0 would be 60 miles per hour, which is 26.82 meters per second, time 1, 0.5 seconds, which gives us 13.4 meters. Okay, so that's the first step. We figured out how far the car goes before you hit the brakes. All right, so let's come back here and put that in right where it belongs. X1 equals 13.4 meters, and I'm boxing that because that's something we figured out as an intermediate step. Okay, so to wrap this up now, we just have to figure out x2, right? That's the total distance the car traveled before you stopped. Okay, now we'd like to use our constant acceleration equations over here. Okay, so we're looking for x2, right? This is one of the kinematic variables at moment 2. So we would solve the problem by relating what's going on at moment 2 to one of the other moments. Now, can we relate what's going on at moment 2 to what's going on at moment 0? Ask yourself, can we? No, because we don't have constant acceleration all the way from 0 to 2, right? To use the constant acceleration equations, we have to connect two moments, which are connected by a constant acceleration all the way between them, right? Right? So between moment 1 and moment 2, we have constant acceleration minus 0.7 g all the way, which means that we connect moment 1 to moment 2 legitimately using the constant acceleration equations. Okay? So we can connect moment 1 to moment 2 using one of these guys, but changing the subscripts so it connects 1 to 2 instead of 0 to 1. Okay, now which one of these guys do we want to use? Let's think. All right. The key here is we don't know what this final time is, and we're not being asked for the final time, right? We don't know what the final time is. We're not being asked for the final time, so maybe we want to look for an equation from that list there that doesn't have any time in it. Which would that be? Time, 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 time. Okay, how about number 4? Let's take number 4, change the subscript so that it's connecting 1 to 2 instead of 0 to 1, and that ought to do it for us. So what we have here is then v2 squared equals v1 squared plus 2, let's call that a12, x2 minus x1. All right, we can simplify this a bit. We know v2 is equal to 0. And now we can just solve for x2 in terms of everything else. Okay, so that's going to give us x2 equals x1 minus v1 squared divided by 2a12. Right, so if you like, you can pause now and do the substitution yourself. What I got here is 65.7 meters. All right, now, if that's how much distance it takes your car to stop, were you able to stop your car safely in the 8 or 10 car lengths you thought you were going to need? Now, to check this out, we're going to convert this into car lengths using a rather generous car length of 15 feet. So here we go. We got 65.7 meters equals, I'll write that as again 65.7 meters. I'll multiply that by a car length is 15 feet, kind of a long car. I'm being generous here. Okay, and we want to convert feet to meters so that we can cancel meters here. And then we got 3.281 feet over meters as our conversion factor between feet and meters. All right, now for this I get 14.4 car lengths. All right, so if you were keeping 8 car lengths or 10 car lengths distance, as many of you said, you did not stop safely, and it turns out that if you're keeping a nice 10 car lengths of distance, you only hit the refrigerator at 44 miles per hour. Of course, if you're only keeping 8 car lengths, then you hit the refrigerator going even faster than that. So there you have something to keep in mind as you're driving this weekend.